I'm going to try to give you some generalized strategies for sketching wave functions in an arbitrary potential. Certainly every problem will be different, but there are some rules of thumb that are helpful to follow. So I'd like us to consider some arbitrary shape in a one-dimensional potential. And this might represent the potential energy curve U of x. And let's imagine that we have a particle whose energy is E. We're going to try to develop some strategies for how it would sketch the wave function for this particle that's bound inside of this potential energy curve. So of course, the location of where it's bound inside is sort of defined by where the total energy equals the potential energy. So as a general strategy, it's best to start with making an arbitrary choice for the energy E, and this defines inside and outside of the box. So in this case, it's better to remember that we have, in general, some amount of potential energy and some amount of kinetic energy. The places where kinetic goes to 0, this is inside, and this is outside, this is outside. The second strategy here is to remember that E minus U of x varies with position. And to remember that the wave number, which is 2 pi over a wavelength, is going to equal 2m E minus U square root over h bar. This means that the wavelength is going to vary along the potential, because as potential goes toward energy, this term goes to 0, the wave number goes to 0, and what happens to the wavelength? Well, the wavelength is becoming very, very long. On the other hand, as potential energy goes to 0, E is the same, the wavelength becomes very short. So wavelength will in general change as I move here to the right or move here to the left. The third strategy here is to remember that inside the box, the differential equation for psi looks like so, where k is the wave number, it's a positive number. So this means curvature is always negative relative to psi itself. This means that the curvature of psi of x is always towards the axis. If psi is negative, then the curvature is positive. If psi is positive, then the curvature is negative. And just to highlight point number 2 again, the curvature will sharpen as e minus ux increases, which means that k increases. That's the same comment, that wavelength depends on position. Depends on the potential. The next strategy, remember, is that outside the box, the second derivative is positive relative to psi. This means that the curvature points away from the axis. So if psi is positive, then it looks like so. If psi is negative, then it looks like so. That's the opposite case of inside the box. And this is why we say that we have particle damping as x goes to plus or minus infinity. Next important strategy is that we count nodes. The ground state will have no nodes. And the nth state has n minus 1 nodes. The sixth point to remember is now that the wave amplitude will also depend on potential energy. Why is this? Well, you can think of it using a step type potential. Something like so. A qualitative picture is like so. If the particle is slowing down in this region, potential energy is going up, therefore kinetic energy is going down. Call this region 1 and region 2. In region 2, the velocity of the particle will be slower, and therefore the odds of finding the particle would be more, and therefore the amplitude, which is related to the norm squared of psi, which is related to probability, so it should be larger. So actually, I've not drawn this. I should have drawn that even bigger in this region than in this region. More formally, I'll just write down the qualitative answer. Another way to think about this is to imagine that psi of x looks something like a times sine kx. It would therefore be mathematically true that d squared, that d psi dx, it's a single derivative, is Ka cosine kx. We know that psi and its first derivative, d psi dx, are continuous at boundaries. So in particular, they would be continuous going from region 1 to region 2. And therefore, the following little mathematical identities is going to be held. If I square and sum psi squared plus d psi dx quantity squared over k squared, that equals a squared. Why is this relevant? Well, psi and d psi dx are continuous at this boundary. We know that k, which is 2me minus u square root over h bar, we know that that quantity is discontinuous. Therefore, a should be discontinuous. K is in fact going to shrink. If k shrinks, that means a increase. So the amplitude has to be larger in this region, region 2, than it does in region 1. So that's another important feature that we're going to come to sketch out correctly more and more. And the last important strategy to remember is if the potential has certain symmetries to it, like the potential at positive x is equal to potential at negative x, then the same will have to be true for the probability density. Because the probability of finding a particle shouldn't depend then on where I will find on the positive or negative coordinate, because the potential is symmetric back and forth. But this means I actually have two possibilities for the wave function itself. Because when I take the square root, I'll have a plus or a minus sign there. If it's a plus sign, these are called even wave functions. If it's a minus sign, these are referred to as odd wave functions. And it turns out these will have measurable differences, even though the norm squared is the same for both positive and negative. But we should just recognize that for every potential like this that's symmetric about the origin, there will in general be even and odd wave functions for this potential. So with those few strategies, then, it's possible to sketch the wave function for rather complicated potentials as much as we might like.